So let's have a little look here at this. You might remember that we decided there was a trick, right? We looked at an example where if we wanted to take the limit of a function as, for example, of g of x, as x approaches 0, we've got a problem, don't we, right? So how do we deal with limits like this? Well, some of them are really easy, right? Some of them we can just directly evaluate and get an answer. Well, we kind of talked about this. This has been a few days ago, though. If we get an answer, like let's do a different one.
That's supposed to be 3?
Oh, no, it's supposed to be x.
Okay, just curious.
Sorry. Yeah. Oops. Okay, we could do this limit. The limit of g of x as x approaches 1. What's the answer? 1, right? Everybody agree? 1 cubed over 1 is 1, and that's fine because when we approach 1, there's the point we approach, and the point we approach is the point the ant would actually step on. And so the easiest way to answer the question, where does the ant think he's going to step, is to actually figure out where would he step by plugging in 1, right? Make sense? Okay, but we run into a problem here. Because here, if we try to take this limit, we get an answer that is equivalent to meaning we need to do more work. We don't get a numerical answer, and we even don't get one like 1 divided by 0, or something like that, right? Where we're dividing by 0, we know that the function blows up in ways that we will get more specific about later. But for now, we just know there's no limit, right? Does that make sense? We get some kind of asymptotic behavior and there's no limit there. Either one of those two circumstances, as far as we're concerned right now at this juncture in the class, those are easy. Those are ones that we're done with immediately. We either get a numerical answer or the answer is no limit and we move on. But something like this is different. Because something like this, where we're trying to evaluate the limit at x equals 0, we get 0 over 0, right? And what did we call that? We get an answer that's 0 over 0. No, it's not no limit. It's indeterminate. It's an indeterminate form. Meaning, we don't know. We don't know what the answer is. But there could be an answer. Maybe there isn't, but maybe there is, right? And we've got to find that answer. We had a really interesting strategy, though, for finding that answer. Remember what it was?
It's really tricky. That we're similar, or approaching x's to
Well, okay, so we could do it graphically or analytically. Or graphically or numerically. But the problem with that is, what if the graph isn't obvious?
Didn't
You know,
we factor the equation?
Yeah, we did something. We did something really tricky. We said, okay, let's do something instead. Let's trade this function g of x. Algebraically, I could cancel factors, couldn't I? Everybody agree? So algebraically, I could say this is equal to x squared, right? Everybody agree? But that's a different function. That's not g of x, is it? We changed it. G of x is undefined. If I look at the function g of x, what is its domain? All reals except 0, right? What's the domain of this new function? All reals. So we have to, this new function, something different. Let's just call it f of x, how about? Right? So what did we do? We traded g of x for a new function, f of x, that is the same as g of x. It agrees with it everywhere except one point. What we effectively did is we filled in this point to create a solid function. Okay, why? What's the advantage of that? So we can figure out what it would have been, right? Because if we're taking this limit, you got to really think about this, really focus on this. Think what we're asking here. If we're taking a limit of g of x as x approaches 0, all we're trying to do is we're trying to answer the question, where does the ant think he's going to step, right? by filling in that point and choosing a new function, a more convenient function, we can answer this question about g of x by evaluating our new function at 0. Does that make sense? So f of 0, this is function f of 0 is what? 0. So if f of 0 is 0, then the limit of g of x as x approaches 0 must also be 0. Does that make sense? Very tricky, right? That's a great strategy. Okay? And literally in a math textbook, they're going to call that, we're going to evaluate a limit by finding two functions that agree at all but one point, or some of them might say everywhere but one point. That's our strategy. Okay, let's try that. Let's try it with a different problem.
So if we had that on like a rootable sign or something, and wanted the answer would get 0 in.
Yeah,
Like that's the
yeah,
word.
that's the answer to the limit. Yeah. How about one like this? What if we've got the limit of the function 3 over x minus 2 as x approaches 2? What's my answer?
Undefined.
So what do we say?
It'd be an asymptote.
It's an asymptote. Because our answer, look what our answer looks like. If we evaluate directly, we get 3 over 0, which means what?
Undefined.
Okay, sure, but in terms of what is our limit, done, no limit. Okay? On the assignment, that's what you put, no limit. Okay? How about this one? It's 2. Everybody agree? Done. Right? Okay, let's change it though. Let's make it a little harder. What do I get? If I evaluate directly, what do I get?
You get it over 0.
What do I get? 0 over 0. What's that mean?
Oh, it's
Indeterminate, more work, right? We've got to do something. Okay. So what are we going to do? What can I do to that?
it's a factor.
Okay, I can factor. Yep, I can factor. So I'm going to get the limit of, what does the top factor into?
X plus 1.
X plus 1 squared, right? Good. Over x plus 1 as x approaches -1, right? Algebraically, I can cancel factors. Agreed? So I'm going to transition from this function to a new function that agrees with it everywhere but one point. So I'm going to get the limit of x plus 1 as x approaches -1. And what is it? 0.
Will all the indeterminate answers equal 0?
No.
When we
Nope.
do them?
Not at all.
It's just the example.
Those just happen to.
Oh,
Yeah.
okay.
Okay, so it worked, right? That's our answer. Okay, we chose a new function that fills in that hole, and when you get a 0 over 0 behavior, that means hole in the function. Right, so what we've got to, by canceling the offending factors, I'll call them, we're going to fill in that hole. We're going to choose a new function that fills in the hole. And it's always going to work that way. You get 0 over 0, algebraically, there's always, it could be really hard, but there's always going to be a way that you could deal with the limit analytically by filling in the hole. Okay, let's look at a couple other examples. How about Okay, this guy. If I evaluate directly,
0, 0.
0 over 0, okay, so more work. So what can I do?
Back to the bottom.
Okay, I can factor the bottom. So what's the bottom factor into?
X minus 2x plus 2.
Okay, so what about the top? I gotta somehow get common factors that I can cancel. What do I have to do to the top?
Take a multiply by
Good, take out a -1, exactly. Factor out a -1 and I'm left with x minus 2, right? We agree? So then I can, now notice that those are the factors that are causing the difficulty, aren't they? Right, the ones that I'm canceling. Do you see and appreciate that? That's pretty cool, that it works out that way, right? Why did I get the 0 over 0 behavior? Well, because these are the factors that both go to 0, right? So by algebraically canceling the factors that are causing the problem, I eliminate the problem, right? And effectively, what am I doing? Filling in the hole, right? Do you see that, okay, I wanna make a point here in a second, so we can do this, right? Those go away, and I end up getting the limit of -1 on the top, right? Divided by, that's what's left, okay, divided by x plus 2 as x approaches 2, which is what? -1/4. So that's my answer, right? Think of it this way. If I took this function, if this was f of x, maybe that's g of x, right? If I took this function and I multiplied by 1, am I changing it? No, right? 1's the multiplicative identity. It preserves the identity of anything I multiply it by, correct? Okay, but what if I make that 1 in the form x minus 2 over x minus 2? Then, right, that's f of x. What did I do to g of x by doing this? I multiplied by 1, so did I change the graph in the shape of the graph in any meaningful way? No, right? Shape of the graph's the same, but now because I've got an x minus 2 on the bottom, 2 is removed from the domain. So you see that what I did by multiplying by this function, I created a hole at x equals 2. It works both ways. Make sense?
Is there any reason you would do that?
No, there isn't, right? So we'll want to do the opposite. We'll want to undo the hole, but we don't ever want to create the hole. But I just wanted you to see that, I mean, does that kind of help you maybe get a feel for how this all works? Okay, how about something like this? What am I going to do with try direct substitution? Of course, what happens? 0 over 0, or would be easy, right? But you always want to check that. I mean, don't get in the habit, just because I'm focusing on the problematic ones, you know, if you actually were doing this, doing some math, you always want to check and see if direct evaluation works, right? What am I going to do here? That's really tough to think about factoring that, isn't it? You could make it work, but it's pretty hard. Right? Okay, I can't do that. I can't square both top and bottom because if I'm squaring it, I'm changing the function, changing the shape of the function, right? Does that make sense? I can't do that. All I can really do is add 0 or multiply by 1, right? And not change the function. But I want to multiply by 1. It's rare that we ever add 0. We're going to multiply by 1 in a way that's going to be helpful. Okay, now, why is this a problem? Well, it's a problem because we're getting 0 on the top and 0 on the bottom, right? somehow we've got to maybe change the expression on the top or the bottom in a way that's gonna be useful. Is there a red flag that pops out here that makes this problem especially difficult to deal with, much more so than the last one?
The root.
The root, right? We've got this square root up here that's causing problems, right? If I multiply both top and bottom by some constant, for example, or even by x or something, I'm still gonna get that square root there, right? It's not just that the square root is there, it's that the square root is a part of an expression that goes to zero. Part of a factor that goes to zero. The whole top is a factor, right? You see that? Any ideas? So my goal, as you're thinking about this, my goal would be to somehow change the factor on the top that involves the square root so that it doesn't go to zero. Right? If I multiply both top and bottom by the expression on the top, that's not going to work well, is it? Right? Let's just look at a simplified version. If I have the square root of a minus b, if I multiply that by the square root of a minus b, some good stuff happens when I distribute, right? I'm going to get square root of a times square root of a is a. Oh, that looks promising. But then the cross products are bad. I'm going to get minus square root of a times b minus square root of a times b. So plus b squared. See, I've still got that problem.
Can we just multiply both top and bottom by root of x plus 1? Therefore, just basically moving the root to the bottom of that.
Okay, if I do that, let's just see what happens, right? If I do that, if I multiply top and bottom by square root of x plus 1,
Can you just,
what do I get? Okay, go ahead.
can you do that without multiplying the two also?
No, you can't. You have to distribute it through the whole thing though, right? That's the problem. So if I do that on the top, I get the limit of x plus 1 minus 2 times the square root of x plus 1. And unfortunately, what happens there if I let x go to 3? It's still 0, isn't it? Right?
Can you do square root of x plus 1 plus 2?
Ah, yes. And why do we do that?
Because it gives her no terms.
Good, because if we multiply a binomial by its conjugate, right, then that gives us a difference of squares. That's useful, right? Look at the difference in the patterns. That's a really good idea. See, here's the problem with this. If I just multiply a minus b times a minus b, I get an a squared, good, minus 2ab, bad, plus b squared, good. The squares are good, right? The square terms undo a square root, but that product in the middle doesn't. I'm going to get a cross product that still involves a radical. However, a minus b times sa plus b equals a squared minus b squared. Excellent, right? Squaring a and squaring b is perfect because that undoes the radical, right? Okay, so there's our strategy. When we're faced with a situation like this, we're going to multiply top and bottom by the complex, or not complex, by the conjugate of the factor that involves the radical that's going to 0, right? So we multiply this by square root x plus 1 plus 2 divided by itself, so it's just 1, right? What's that give us? On the top, what do we get? X plus 1 minus 2 squared, which would be 4, right? Everybody see that? I'm going to get that, a squared minus b squared, right? Now, the bottom looks bad, and you might be thinking, oh, well, what did we do? We just shifted the problem somewhere else, but let's look at the bottom. On the bottom now, we get x minus 3 times the factor square root of x plus 1 plus 2. In the limit that x goes to 3, notice that this factor does not go to 0. Everybody see that? Okay. Well, if we simplify, what do you notice happening here? If I simplify the top, what do I get? X minus 3. Right? So there's my 0 over 0. Perfect. I can cancel the offending factors, the ones that are taking us to 0 on the top and the bottom. You see what I'm saying?
And now that will make it 0, so it's fine.
Exactly. So we fill in the hole, right? This is the step when we cancel the offending factors. That's the step where we fill in the hole, right?
Like, can't you not have a square root on the bottom of a fraction to denominator?
Well, no, it's fine. It's fine. That's really a hokey rule. You can, and what difference does it make anyway? Because we're evaluating this at 3. See what I'm saying? So we end up then with, now if we take our limit, that's what the words we use in calculus. If we take our limit, that means we're going to evaluate it at 3. What do we get if those terms are gone, or those factors are gone?
4.
I get 1 on the top, right, divided by the square root of 4, which is 2, plus 2, 1/4. See how that works? So that's the reason I picked this example is because it illustrates a new technique, right? If we just got a rational function, polynomial divided by polynomial, we just factor top and bottom and cancel factors, right? That's probably the easiest situation.
What would you do if you had 2 holes in the equation?
Well, okay, that's okay. Now, here's why that's okay, because we're only approaching one x value, right? So if we look at it graphically, it's a good question.
But so 2 holes would never matter, though, for finding limits of roots.
Right. We only care about the one that we're approaching. So if this is my function, let's say we've got a hole there and a hole there, right? If this is the value c that we're approaching, we got to fill that one in to answer our limit, but we don't really need to worry about that one. Because as x approaches this value, that one's not causing a problem, right?
How do you even get a function with 2 or more holes?
Oh, we will.
That's,
We'll get lots of them.
well, it wouldn't be 2.
Yeah.
Alright.
Well, so what if I had, we could build one right now. We could work backwards and build one by just saying this. What if we have f of x equals, in factored form, x minus 1 times x plus 2 times x plus 3 divided by x minus 1 times x plus 2. Got holes at x equals 1 and x equals negative 2, right? So if I fill both those in, if I fill in both holes, what's g of x going to be? Well, just the line x plus 3. Okay. So what's this look like? It just looks like a line with a y-intercept of 3 and a slope of 1, except it's got holes at positive 1 and negative 2, right? Okay. All right, another one. So, real quick, to recap though. So why did we do this problem? To illustrate our new technique, if we're faced with a situation where we have an indeterminate form that involves a radical, our strategy is to multiply top and bottom by the conjugate of that radical factor, right? Okay? How about something like this? What do we get? 0 to 0, right? Indeterminate. So what do we do? Well, really all we do here is we simplify. This is just like a different starting point for the first sample problem that we dealt with, which was a rational function, right? All we've really got to do is just simplify this thing and turn it into a rational function and then deal with it like we normally would. okay? So how do we simplify something like this? Talk me through that. What are your ideas? Some big ugly deal.
You could just multiply the thing by x over one, you know, get rid of that top bar.
Okay, so eventually we're gonna do that. Whenever you have a function that involves fractions on the top and the bottom, our overall goal is this. We want to simplify the top into a single simplified fraction, bottom into a single simplified fraction, and then flip and multiply by the bottom, right? So what about the top though? The bottom's easy. Bottom is just x over one, right? That one's done, but the top is not. The top, we've gotta turn that into a single function. How do we do that? How do we find a sum or a difference of fractions?
Well, would it just be blatantly 0 over x?
What do you mean, 0 over 0, right? Right now? If I let x equal 0,
No,
I get,
but without the x, when it's still just with x, it's, if you subtract 1/4 from 1 over.
no, you can't do that. See, because 1 over x plus 4 minus 1/4 is nothing, right? We can't,
But isn't it 0 over x mathematically? Like, isn't that just fact?
how are you getting that?
Well, because, don't you have, oh, never mind, because that'd be 0 over, it's been a while since I've done fractions.
Right, it's probably a lot of you, but we gotta get, fractions are real and we deal with them all the time. So what do we do when we're trying to simplify a sum or a difference involving fractions? What do we always have to do? Common denominator, for sure, right? So what's our common denominator gonna be? Well, the least common multiple of x plus 4 and 4 is the product of x plus 4 and 4, right? Everybody agree? So my least common denominator is just gonna be 4 times the quantity x plus 4. So what do I have to do to the left fraction? Multiply by, or 4 over 4, multiply by 1, right? So we've got, right? What about the right fraction? Over x plus 4, right? Okay, so then on the top, because really the top's the only place we're working on this one. What do we get? Well, we get a common denominator. So the denominator of our fraction on top is just gonna be 4 times x plus 4. Resist the temptation to expand. Because why? Well, we don't need to. This thing is gonna sort of self-clean when we take the limit and let x go to 0, right? There's no need to do all that extra algebra. Just more of a chance for making a mistake. It actually makes the process harder because you get the x showing up in more places lots of times. So leave the bottom as it is. What about the top? So I'm gonna get 4 minus the quantity x plus 4, right? Everybody with me? Okay. And on the bottom, I've just got x, right? Okay, so what do we get? If I simplify the top, okay, the 4 and the 4 cancel, I just get negative x. If I distribute to negative 1, okay? So I get negative x over 4 times x plus 4, all divided by, call it x over 1, right? So then, now what? I can flip and multiply by the bottom, right? Because I've got this big fraction on top and this smaller fraction on the bottom.
Like keep change flip,
What's that?
keep change flip, isn't that what it is? You keep the top, change the sign, and flip the bottom, or is it the other way around?
I've never heard that. You just flip and multiply by the bottom, just multiply by the reciprocal. Is that what you mean?
Yeah, keep change flip.
Okay, there you go.
That's what we call it, back flip. I know
Okay,
you're-
that works. I mean, if that works for you, that's fine. So then we're gonna get the product of the factors, negative x over 4 times x plus 4 times 1 over x, right? And when I multiply fractions, I just multiply straight across, right? So really all I've done is I've just tacked the factor of x onto the bottom. So now what can I do?
4x.
Couldn't you just,
Or minus
couldn't you eliminate the two x's? and
Exactly,
eliminate-
right? And I have to have that step, don't I? the way, and we could have predicted what it was gonna be from the very beginning, right? Because what is the value of x that's going to 0? Well, 0, right? So then we know that the factor x minus 0, which is just x, has to be canceled top and bottom, right? To get rid of the 0 over 0 behavior. So there it is. Here is the step where we fill in the hole, right? Those go away, and we're left with the limit as x approaches 0 of -1 over 4 times the quantity x plus 4. So now in the limit, when we take our limit, we let x go to 0. When that goes to 0, what are we left with? -1 over 16. There it is. Make sense? Right? Okay, so is that really, I mean, is that really a strategy? Well, not really. What did we do? We simplified the whole thing, and then we canceled the factors, right? But because we were dealing with a whole, convoluted problem involving fractions on the top and fractions on the bottom, there just was a fair amount of simplification to do. But really all we did was just combine, common denominator, simplify the top into a fraction, simplify the bottom into a fraction, flip and multiply, and that's where the factor comes. Okay. Okay. What are we at here? 15?
Yeah.
Darn it, anyway. Okay, let's do one like this then. How about, what's that?
Do we have homework tonight, or are we just learning?
No, I'm gonna put the assignment up. Yeah. Have I not already put it up? 1.3? Oh, I haven't. I haven't turned it on. I made it, but I haven't turned it on yet. I'll turn it on now. Okay, so what about something like this? What is the variable of the limit? H. Insofar as the limit is concerned, x is a constant here, right? The limit is acting on the variable h. We're taking the limit as h goes to 0, right? Not as x does something this time, right? A little different. So think what's going to happen here then. We're somehow going to have the h going to 0 part cancel, right? So you can kind of predict, we're going to need to be able to cancel an h divided, we're going to have an h divided by an h that we can cancel to get rid of that indeterminacy, right? It is indeterminate though, isn't it? If I let h go to 0, I get 0 on the top and 0 on the bottom. So what do you think I do here?
You factor you do the square of the
So-
x plus h, and
yeah.
then you get x squared plus 2hx plus x h squared, and then the x squares cancel out, and then you take out h of that.
Good, so that's very good, you're looking at, but the main thing is, without all the specific steps,
Sorry. it
there's no fancy, I mean, all we're doing is just expanding the top and simplifying, right? And then when we do that, we're gonna have to be able to factor this. It's guaranteed to work, it has to, right? Because we get 0 over 0.
Why are we doing it? We already know it works.
Well, but because we don't know the answer. We gotta get the answer.
But the answer doesn't matter.
Oh, the answer matters. So if we expand this out, you tell me right now, using the binomial expansion, what is the quantity x plus h squared?
x squared plus 2hx plus h squared.
Good. Minus x squared over h, right? Okay, so what's happening now? Does,
There you go.
Cancel out the x squared,
Okay,
do
good,
that,
good.
and then you can just do divide by the thing.
good, so Now, you can I want you to kind of see this unfolding here. When you see something like this, look at the expression on top. What we call the naked terms, that's what I call them, the naked terms, the ones without the h go away, right? They're gonna cancel by addition, they add to 0. We don't see that very often. Usually we cancel by dividing. We cancel the 1, usually, right? Here we're canceling to 0, those go away. What do you notice? All of the remaining terms contain a factor h. So I should be able to factor an h out and cancel with the bottom, right? Okay, so then we end up with the limit of, if I take an h out of the remaining terms, what do I get? What's left?
2x plus h.
Over h as h goes to 0. Well, let's fill in our hole. Because we had a hole at
H.
h, right?
So the limit is just 2x.
So yeah, so the limit then, so we end up with the limit of 2x plus h as h goes to 0, but as h goes to 0, that term goes away. So it's 2x.
Some days it's been my friend.
That's good. No pain, no gain.
Yeah.
One thing we did last year, when we could understand what you were saying, we felt so smart.
Well, now you got it, right?
Good timing.
Yeah.